Let's begin. This is a rather remarkable talk. Many have been, but what this is about is Jennie D'Ambrose is bringing these kinds of dynamic situations into her calculus class in a comfortable manner. And we have instances inside SIMIODE, and I think what she can do for us is give us the courage to try this in a class that's lower than you might think, and without killing them and without threatening them, but exciting them. So Jennie, we turn the platform over to you.
Great, thank you so much. So I'm going to run through two SIMIODE scenarios that I modified. And the first one here was the original version is from Brian Winkle. And I simply modified it in order to introduce it into my Calculus 1 class. And as far as prerequisites, like what would we do before we do the SIMIODE scenario, I literally just get through the differentiation rules, product rule, chain rule. We do the standard section on related rates. I think I usually have my midterm at that point, and then the next class, the students are very tired of taking exams at that point, and then we try one of these projects. So I'm just going to run through and sort of explain how I modified the project so that to make it suitable for Calculus 1 class. So here's a little bit of data collection. Here's just something that I did as I had the students. You can see that the numbers are kind of gradually increasing, and I have them put their own numbers in. So as part of the teacher resources, I actually have a little octave script that will generate, if you're grading these, the octave script will generate the solutions to make your grading process easier. But I wanted to give a way where, not every student is having exactly the same numbers. So I have the students input what they think are reasonable numbers here. And then this is the area of the oil slick that's getting bigger. And then they calculate the difference equation and or the discrete derivatives and go from there. So here they fill in their little table of the change in y over change in x's. And I'm literally taking the perspective that so this is how I'm thinking about this is, how would I teach this modeling scenario if it was the first day of differential equations class and the students didn't know what a differential equation was? How would I just have them jump into this scenario simply only knowing what they know from calculus, just basic, derivatives? So I walk through what is the derivative of e to the 2x, what is the derivative of e to the minus 3x, and I kind of walk through this process of, hopefully from the student's point of view, helping them to realize that y prime is equal to 2 times y, kind of like guiding them very slowly to solve their first differential equation in Calculus 1 class. And then we utilize the data that we have from these tables, which is a little bit customized per student because they put their own values in there, as I was explaining before.
Jennie,
Go ahead.
Can you just back up and tell us in this scenario what's given and what they're trying to do?
Sure. So in this one, the oil slick scenario, basically the area of the oil slick is given to you. And the very first step is to just calculate the derivative, and then we'll get a differential equation for that oil slick, and then we'll go from there. So as we go through here, I have the students use just, any of your favorite curve fitting website that you come up with. I'm sure that there are others than the ones I link to here. In other words, this is going to be modeling the data of the oil slick. And once the student, all they have to do is model it with a straight line. And rather than having y is equal to mx plus b, your y is the a prime and your x is the a. And there's your differential equation, is a linear first order constant coefficient differential equation for the area of the oil slick. And then at that point, I show them that, if you have y prime is equal to k times y plus b, where k and y are constants, that this is how you solve the differential equation. And I kind of walk them through it basically like guess and check. I don't do any separation of variables here because this is a calculus 1 class. It's literally just guess and check for the differential equation. I walk them through it slowly, like with some examples. And then finally, we get back to the differential equation for the oil slick, which follows the same pattern of that first order linear constant coefficient. And then they can utilize the solution from their sort of guess and check exercise. All they have to do is change the numbers in order to solve the oil slick problem. They just have to change it so that it works according to the numbers in their situation. And then we kind of have some standard questions like making predictions based on the differential equation. And this is the part where I did see the students kind of that light bulb go on. I think when you're in the process of collecting the data and sort of explaining to the student what a differential equation is, and then modeling it with the straight line, and that process, the student can seem a little confusing to the student, or they're following your guidelines. But once you get to the making predictions part, this is the part where I had like 5 different students say, "Oh, professor, we can just use the function that we solved to make predictions, right?" I said, "Yeah, exactly." So that's the part where they started to get excited because they could see, sort of, the outcome of using the differential equation. And here there's just more questions like, okay, provide a sketch of the function. I like these questions. So if nobody cleans up the oil, how big is the oil slick going to get? And here I like to put, limit as t goes to infinity so that students understand, limits actually mean something. It's telling you what's happening to the oil slick, over time if nobody cleans it up. And then finally, I have some questions here about, how much time will it take in order for the oil slick to be, a certain size, and then I just want to jump to the end here. One of the things that I put into this modeling scenario was trying to estimate the cost of cleanup. Sometimes with these scenarios, I don't want to, if we're talking about like an environmental disaster, I want to at least try and have a modern, take on it to ask the students, if it's this many square miles of an oil slick, and let's just suppose that, renting a boat to clean it up costs this many thousands of dollars, how much money does that cost to clean up the oil slick? So the students can kind of think about, the real life implications. So that's my first SIMIODE modeling scenario that I modified. I can go over the second one probably, which is the cancer, but I'll just pause here real quick because I wanted to make a little bit of a comment here about, obviously there were parts of doing this project that I was really satisfied with, kind of having the students go through the process. And I love it when they ask me those questions like, "Oh, wow, we can make predictions now, right, professor?" And I'm like, "Yeah, great. That's exactly what we're doing." I loved going through that process with my students. But I also felt like, so this is something that I did last year. It was last spring. And this spring, I'm teaching Calculus 1 again. And I was thinking about ways that I can, change my approach and make it even better, which is that I was thinking that maybe I should ask my students this semester if they can kind of author their own questions, because there's something about, the professor providing these, 10, 15 questions for the students to answer, that they just go into like automatic answer mode. Okay, this is the answer for that. This is the answer for that. This is the answer for that. But this semester I was thinking maybe I would give the students another task, which is to, I'm going to have them, I was thinking maybe I could have them pose at least like 3 new questions. Maybe 2 of them are questions that you actually can like ask and answer, like about the oil slick, and maybe describe like what implications that has for real life. And I'd really like to ask them to pose a question that they can't answer, and what implications that has for real life. So I was thinking of, developing, into my like pre-formatted questions, the ones that I came up with, a little bit of an extra, a little bit more interactive type of component to the scenario as well, to see if I can improve my approach this semester. But anyways.
So what, just pause.
Yeah.
Any encouragement, any suggestions? It's a good
Yeah,
idea.
I would be more than happy to take, see if people have ever used an approach similar to that, or if people have suggestions for how, how to engage the students even more. That would be great.
I've got something. I think that's a really good idea, and it is sort of similar to the whole idea of project-based learning, which I think goes really well with the idea of modeling first in teaching. The only thing I would say is if you want to get those questions from them and you don't want them to just be kind of variations on the ones you're asking,
Right.
I would
Yeah.
encourage you to, before they even see any of your questions, encourage them to ask questions about the oil slick in this example, or whatever project you're working
Sure.
on.
Yeah,
And
maybe
then
what
you'll
I
get
could
more.
do is like just provide them with the first 2 pages so they could kind of know what's going on with the oil slick, and then
Exactly.
like not show them my question. Yeah, that's a good idea. Mhm.
Exactly.
Yeah,
But I
yeah.
think it's a great idea, and definitely
Yeah.
project-based learning, fundamental stuff for sure.
Mhm. Sure.
Yeah, and they have fun being the teacher.
Mhm.
I mean, in a sense, and some of them, well, many of them will come up with better than what we have. I mean, at least
Right,
I.
right.
All right, well, any other comments? If not, we'll go on to your second.
Sure. Yeah. So I do have a second scenario that I modified specifically for Calculus 1 class. This one is from Ju Wang at Union College in New York. This one is about cancer, modeling cancer tumors. So the first part just assumes that it's an exponential model, the tumor is growing exponentially. And again, with the limit as t goes to infinity, emphasizing like what that means. It means, how big the tumor is going to get over time. And then I emphasize here how unrealistic that is, that the size of the tumor goes to infinity, right? So let's think about that. Is that realistic? And then I use that to modify, just a basic explanation about the growth rate minus the death rate, in order to come up with a new differential equation that could perhaps be a little bit better. Now here, excuse the train, I apologize. Long Island Railroad. But again, because this is for Calculus 1 class, I didn't, I feel like if I try to do separation of variables, we're kind of going to have to spend at least, a good 45 minutes, doing separation of variables. So I took a different approach here, which is just simply to provide them. I'm using a guess and check approach for the differential equation. So I'm just providing them with the solution to the differential equation, but still asking them to verify that the left-hand side is equal to the right-hand side, so that they kind of get the idea like, oh, the function has to satisfy the properties of the differential equation. So I walk them through that process on this page. And then there's another modification, which is another improvement of the model that is run through here. But again, I just provide them with the solution and then have them check it. And then I thought I love this diagram. It's so cool. Like, it's all of the different, ways that you can use differential equations to model the tumor growth. And I make sure to point out to my students, well, we only in this class, because I'm such a nice professor, we're just gonna do like a couple of these. We're not gonna do the entire diagram. But if you were doing really rigorous research, or if you had a lot more time to devote to this project, here's all the different types of differential equations that you could potentially use in order to model the cancer growth. So that is mostly there, because it's fun to look at. We're not really doing too much with that diagram. And then here is just a fitting of data that we have. I think the table is here. Yeah, we have data that's just provided. This is provided in the original draft from Professor Ju Wang. And we're going to use that data in order to decide which one of the models that we looked at in this, exponential model versus this one is actually just a standard first order linear constant coefficient versus the Gompertz model, like which one of these models fits the data the best. And then the students can do the parameter estimation and decide, with least squares, like which one of these models fits the scenario closest. So again, I think I had a similar experience with doing the cancer research, the tumor growth scenario, which is that the students were, received pretty well the project, but because it was my first time doing a project like this, I was a little bit concerned that I'm posing all the questions and the students are just kind of going through my activity rather than posing the questions themselves. So that's what I'm working on this semester, is to see if I can try and improve my process and get more engagement from the students. Obviously, my goal is to make it so that it's digestible for them. In the previous academic year, I just had the modeling scenario, literally one class is we just went through the differential equations and making sure it satisfies the differential equations as well as the least squares fitting. And I easily did all of that in one class with no lecture. The students just sat there, with the activity sheet and talked to each other and like worked in the classroom. This semester, what I'm going to do is, like I said, try to get more student engagement in terms of formulating the questions themselves. And I'm actually going to replace one of my exams with it so that I can probably devote like a maximum of 3 class sessions to the whole project modeling, process. And this semester, I'm not tied to doing the same scenarios as I did last year. For the oil slick or the cancer growth, I was even thinking that maybe I could just direct the students to the SIMIODE modeling scenario website and actually have the students look through the different scenarios and see if they can suggest to me, oh, we'd like to work on this scenario. I think that might be a different approach, which is to kind of let the students select what scenario that they want to work on. Because one of the things that I'm kind of concerned about with these types of projects is, let's just suppose that I have a bunch of computer science students in my class, and then I just happen to pick the cancer growth, which maybe the biology students would be super excited about, but I'm not so sure the comp sci students would care too much about the cancer growth scenario. So I thought maybe I could get a little bit more like student voice into the projects by actually having the students, browse the scenarios themselves and tell me what they think and have it be a little bit more interactive. That's definitely way more open-ended than I had attempted last year. But I'm going to give it a try and see how it goes. And maybe I'll have part of my students working on one project and part working on another, but we'll see how it goes.
Terrific. How about some others? Have you backed in material from a differential equation course into a calculus 2, and even so far as a calculus 1? After all, in calculus 1, we're about figuring out the rate of change. And what we're doing in differential equations is saying, if I tell you something about the rate of change, can you tell me something about what's going on? So it's not unnatural, but it's not what we normally did or do. And I think Jennie and Victoria, who's going to be speaking next, has done that in pushing them back.
Yeah, I would be really interested to hear what approaches other people are taking, because I feel like I'm kind of going blind here. I'm just trying things out. And, sometimes it works out, sometimes it doesn't work out. But
we're not trying to rush the student either. We're just trying to show them what the future might have, and with rich examples.
Trying to inspire them more than not to overwhelm them, but to inspire them, because, if you don't have any of this stuff in the classes are just manipulating formulas, so just trying to improve on the pedagogy.
Brittany asks, she loves the oil slick modification. Is it on SIMIODE site? And the answer is yes. The original oil slick model was not mine. It came from a Canadian little monograph. And if you haven't looked at it, I'd suggest you look at the original, because what it tells you is it really challenges students, not because it's hard mathematically, because they want to plot. And what they cannot do is they cannot plot oil slick size versus time, because all they have is the size of the oil slick and then 10 minutes later. And then who knows when size of the oil slick in 10 minutes later, because the photographer did a lousy job, didn't write how often. So now all they have is a bunch of differences. So they have to deal with differences early on. And I think that's obviously what caught Jennie's attention, was saying, I know where we first encountered differences. And so if you've not used that oil slick and or Jennie's modification, doesn't take long. It's frustrating, and the students will realize they can put together things. And the one that I wrote up, I've been using it for like 30 years. And every year some kid comes up with, well, look at it this way. And I went, I never did. So differential equations in calculus 1, who would have thunk, right? But here we are. Any other comments, suggestions? Jennie's put the site up. Okay. Well, thank you very much. We appreciate your taking a risk in your own teaching and then sharing, and we ought to hear back from you in the future about what kinds of questions they asked, because any one of us who poses the model should immediately ask questions of it. Does it, can it, what about initial conditions, etc. So
thank you.
Thank you.